In this video, we're going to talk about pore strips in Adapt PTRC. Adapt PTRC is a 2D program using the equivalent frame method for two-way slabs, and we're going to show how we can model two different tendons, allow for a pore strip, and allow for the program to calculate reinforcement through the pore strip. So let's go ahead and get started. And we're going to be using Adapt PTRC version 2019 build 1. We want to make sure, because this is a post-tension slab, we select this option here, the first option. And I'm going to directly go into the input window. And we're just going to set up an arbitrary 7-span two-way flat slab. Before we actually do that, we're going to just sketch kind of what we're talking about. So in elevation, let's say we have multiple spans here. And in this span, this is a 4-span, we're going to actually put a pore strip here. So this is an elevation. We have maybe a 7-inch slab. We're going to assume that these spans are all 30 feet through here. And here we're actually going to put a pore strip. So this pore strip might be, let's say, 3 to 5 feet wide. And we're just arbitrarily placing it kind of at the center of span. That may not be the actual place that it's positioned. It might be shifted towards a column or maybe a moment inflection point, but for this example we're going to put it right in the center of span. And another assumption we're going to make is that this pore strip is shored until it's poured back. So after we stress both sides, and we're going to use blue here, we're going to say there's a tendon anchored here at the face of that pore strip. It's stressed, and then on this side this tendon is stressed. And after those two tendons or sets of tendons along the pore strip are stressed, we come back several days later and we pour this back. And we have, reinforcement passing through here that's going to take care maybe of the flexural demand across this location. And so we're going to assume that for our model, we're really just representing the final stage of this strip, kind of the as-built condition of the strip. And we're capturing that through this particular model. You could build multiple models that might be required to capture different stages. For example, if the shoring is not here, and this is a cantilever, let's say left, and a cantilever right, we might have to build 3 models. We might have to look at model 1 on this left side, model 2 on this side. Those are kind of completed in different stages, and then model 3 is the full system again. So we're really looking at model 3, assuming that this is short. And what we're going to focus on, really how to set the tendons up here. We have basically 3 tendon types in this program. There's tendon A, there's tendon B, and there's tendon C. Tendon A, and all 3 of these tendons can be classified using different shapes per span, so that we might have a reverse parabola, a straight shape, a partial parabola, simple parabola if we zero out the inflection points. So these allow the user to enter different shapes. One of the restrictions, however, is that tendon A, I'll go ahead and put a square around tendon A. Tendon A has to be modeled end to end. So in this program, which is primarily built for post-tension structures, tendon A goes from this end all the way to this end. It could be a dead live, it could be live live, or live dead in terms of the anchorage. And here I'm just drawing these flat. In reality, they're going to have some sort of shape to them. So because tendon A passes through this pore strip, we can't really use it. So we're going to actually set that to 0. That will have a force of 0. And then tendon B is going to have a force of something greater than 0. Tendon C will have a force of something greater than 0. And we can actually tell the program where to terminate these 2 tendons. So that's really what we're going to be doing here in this model. So let's go ahead and start with the input of the model. I'm going to use a two-way slab. I won't go through all of the input. We have other tutorial videos that kind of cover a lot of the input of the structure and different settings that can be made analytically, geometrically, or for design. We're going to just bump this up to 7 spans. These are all rectangular sections, and I'll just use the typical entry here to fill out this model. So we'll say it's 300 inches wide. The height I'm going to say is 7 inches, and I'll set the reference height here equal to 7 inches. That means that the CGs are all measured from the bottom of the slab upward. Everything's positive upward. If I left this at 0, everything would be negative downward from this reference line. So we want to push that up slightly, equal to the depth. So this is our system. We're actually going to put that pour strip right here, and we designate that essentially by classifying the tendons and the way the program treats the spans and the different design cuts in the span. So we'll go here and add some columns. I'll just do lower columns. We'll assume that these are all 10 feet, and we'll say they're 22 by 22 wide columns. So just a simple frame. I could do columns above as well if needed. We'll do just columns below. For loading, I'm just going to turn off the skip loading for now, and I'll say that all of the spans have a superimposed dead load, and this is a uniform load. I'll just type U there. This will be 20 PSF, and we'll say that the live load is going to be 50. I need to make sure I change this to live load classification. The self weight is automatically calculated by this setting here, and I'll just leave the material properties as they are, just the defaults. We'll skip over here to, these are just some targets for the post-tension design, the allowable stresses, compression, tension, and then also pre-compression and dead load target. This is dead load balancing. So we'll leave those as they are. We're going to be using the effective force method. We could use calculated force. The same approach would apply for either method. One is just using the average force after all losses. So this really is where we start to designate kind of what shapes we want in each of the different tendon types. We know that tendon A is going to be set to 0, so I'm not too concerned about these definitions here. Tendon B, we're actually going to again model from, this is span 3, this might be anchored at, let's say, 3.25. So we're saying that 25% of this goes into span 4, and then on this side we're going to say maybe 25% comes from this column to the left and anchors here. So 50% of the span length is this pour strip. Now the user would want to make sure that that really correlates with their intent in terms of the design, but this is again just some arbitrary settings. And so for tendon B, we're going to be using span 1, 2, 3, partial 4, and then over here for span or tendon C, we're going to be using span 7, 6, 5, and partial 4. So make sure you have these settings correct. Right now we're using a reverse parabola. I'll leave this alone. We have inflection points. This setting here, option for tendons, this is really where the program defaults the termination of the add tendon. Tendons B and C are really considered add tendons. So this is saying by default, just use 20% of span 4. So this would be 6 feet from this column to the right, 6 feet from this column to the left. You can change that in the recycler, so don't really worry about that too much. We can always modify that once we get into the design of the PT. The shape of tendon extensions is important also. So when this tendon, I'm going to blow this up a little. Let me use a different color here. I'll use the black color. And so we have a column here, and I'm going to just cut that off, and the tendon's kind of draping through here, and then it just comes here and it stops. So the question is, and this could be a live end at the pour strip face. This is like the pour strip here and over here, and we have another tendon here. So at this location, do we want this to be anchored at the CG? So this depth, this is 0.5 H and 0.5 H. This is rectangular, so we're just saying half and half. Or do we want it to follow the shape of the parabola? If it follows the shape of the parabola, this tendon really might be anchored here. So you might be above the CG. So because of that, you have some eccentricity here, and that eccentricity causes some moment that's induced at the anchorage location. So make sure you make the right setting there. We're going to use force anchor it at the centroid of the slab, and that affects how the program calculates the equivalent loads from the post-tensioning that it applies externally back on the structure. Okay, the rest of the inputs we'll just again use the defaults. I'm actually going to turn this off for curtailment. We're going to review some of the reinforcement output, and then we have our typical combinations that we're going to evaluate. So let's go ahead and save this. Alright, and after we save that, we're going to run the model. So we're going to execute the model. The program is going to try and design the post-tensioning using tendon A. So this means that it thinks that the program, or it's using assumptions that everything is post-tensioned. And so it gives us a design. And we can see, if I immediately go to graphs inside of the recycler window, we can see that the program, this red is tendon A, and you can see it goes from end to end. And the force in each span is around 690 kips. That's shown here. This can be changed. This is the profile. These are the CGs, the control points for the tendon: high point, low point, and anchorage point. But what we want is, we really want this tendon to stop here and here, and not have this pass through this pore strip location. So in order to do that, we know that for this design, we know that from the we said about span 3.25 to the left and 3.25 to the right. So really here and here, this is the required force. This is really what the program has picked to get this number here in order to meet precompression, balance loading, and allowable stresses. So we know that this is actually controlling. This 690 here is controlling this side, 690 there controls this side. It's symmetric. And so what we're going to do is we're going to say, well, let's go ahead and zero out the force for tendon A. We don't want to use tendon A, but we do want to use tendon B and C. So we'll go to tab number 5, and I can press the control button on my keyboard and just slide this over. Okay, we could slide one end, slide the other end. This could actually be internal to the ends of the system. So then I could slide this end. If we press shift, we can actually change the assumption for the anchorage. So I could anchor these internal instead of external. I'm going to actually switch that back. We're going to go to a dead live on tendon C, and then live dead on tendon B. Now sometimes it's hard to slide this right to the exact location, so I can key this in also. I'm going to say that this stops at 3.25, and over here this is going to be 3.75. And these are the two termination points for these tendons, these add tendons. And once I set my extents of the tendons, I can go back to tab number 1, select tendon B, and I'm just going to enter a force here. We'll say 690. And notice that that actually picks out the spans that we're going to be assigning this tendon to. Let me make sure that that's proper. If you have it partially in a span, the program still considers it, but you actually enter the force for the spans that the tendon is completely through. So that's why when that was slid a little bit to the right, I couldn't enter a force in this first cell. Now I can, so I can go back and say, no, this is 690, and then I can fill out my control points for tendon B. Remember, the tail by default is going to be cantilevered down from behind the support, so we don't have anything in span number 4. Coming over to tendon C, I'll do the same thing. We'll say set this equal to 690. I can set up my control points here. Once we're done doing that, then we can recycle. So I'm going to recycle this. Now we have a bunch of no goods. So the program still thinks that this entire system should be checked as a post-tension system. So we can see clearly now. Let me go over here to this graphical view. I'm going to right click and maximize, and we can see the red is tendon A, that's set to 0. This one actually terminates here. This is tendon B. This one terminates here. This is tendon C. So there's a gap right here with no post-tensioning. And if we prepare a stress calculation we know that if there's no counteractive equivalent loading from the post-tensioning, we're going to get significantly higher stress than if there was counteractive loads from the PT. We're not doing any load balancing essentially. So at that location, you can see we have high stress, and that's okay. This is not being designed as post-tension, so this exceeds the allowable. That's that gray envelope there. And so therefore it triggers this stress problem, this tension stress problem. It says, oh, for total stress at this location, you're over, your coefficient is 8.68 times square root of f prime c, which exceeds 6 square root of f prime c, and it flags it. And here I'm going to ignore this. This is like right on. That's more of a convergence to the solution there. But right here we're over because that's in the pore strip. Sustained, again, we're over slightly without any PT. We're ignoring that. This is actually an RC section of the design, let's say. So we're going to get overstress here. That's expected. That's where our pore strip is. If I go to the top fiber, notice that our compressive stress is actually okay for locations where we have compression. We would expect that top fiber at midspan. Top fiber at support, we would expect tension. So we have tension, but it's not over the allowable. It's right on the dot there and there. That's what was shown really here. It's 6.05. And we could do that for other combination. We could do it for sustained. You can see there's the overstress for sustained. Down in the bottom graph, we can actually see the force. This is the PT force applied, then it drops off drastically, kind of falls off a cliff there. And that's where we have no PT. This is the pore strip right there. So if we come back over, the user has to make some judgment as to what's going on here in this heads-up display. PT force minimum is no good. Why is that no good? Because we have a location here, span number 4, where we have basically no PT. The center of span 4, there's no precompression, so it flags this. We know that that's the RC location. Maximum PT P over A, that's flagged because if we use 690 kips, we're over slightly from our target of 300. So this can be likely justified, kind of a mix between we're slightly over the actual allowable precompression that we've targeted, and then we have no precompression in the pore strip. Balanced loading, we can see the minimum there is 0% in that same location, so that's again due to the pore strip. And then we talked earlier about stresses. So if we're looking just at the left and the right side, then this is technically a compliant solution for the PT system. We're going to go ahead and exit. We're going to say this is what we want. We're going to exit out of here. And the last thing I'm going to show really is just the reinforcement, how to interpret some of the reinforcement that's needed for this system. So if I go into builder sum and let's say I look at strength max, this is strength to max, and we can see here are our tendons, here's some reinforcement. So at the pore strip, everywhere else we have enough capacity from just the post-tensioning, except for this location here. We need reinforcement there because this is being designed as an RC section. The program breaks every span up into 20 design cuts. There's 20 data points or data cuts along the span, and these particular locations we actually need reinforcement because there's nothing there. There's no post-tensioning there, and this is the amount of reinforcement needed for this particular combination. We could look at other combinations. Strength 1, this is more reinforcement. This is actually 1.2 dead plus 1.6 live, and we need additional reinforcement in some other locations here at this higher level of factored load because the post-tensioning itself doesn't give us enough capacity, so we need some more reinforcement here. But this is for that RC location. And then for minimum reinforcement, you can see this is really based on post-tensioning two-way slab prescriptive reinforcement here at the bottom, because the stress level may be low enough in this particular condition. We don't need any reinforcement at the bottom in these other spans, except for here again, this is an RC span, so we need essentially minimum temperature steel, shrinkage steel for this location. And this should equal, for example, 0.0018 times area gross for example, for ACI code. This is being designed at ACI 318. If we go to service 2, a similar check. Now we actually need some minimum reinforcement in positive flexure zones on these end spans. Here the stress exceeded 2 square root F prime C on the bottom fiber, so that reinforcement kicks in, and then again we have a need for minimum reinforcement temperature shrinkage for this RC zone. So that's how we can go about modeling and evaluating let's say a two-sided condition with a pore strip in the middle in ADAPT PTRC. If you have any questions, please contact us at adaptsupport@risa.com. Thank you.